This is a revision video for P5D, Actions and Reactions, Momentum Changes and Conservation of Momentum. Before we start talking about actions and reactions, we're going to recap forces. A force is a push or a pull. A force is measured in newtons, and most objects experience forces even if they are not obvious. Forces can change the shape of something, change the speed of something, or change the direction that something is moving in. There are contact forces. These forces have to touch an object to affect it. Examples are friction, water resistance, air resistance, and upthrust. There are also non-contact forces. These are forces that can affect an object without touching it. Examples of non-contact forces are gravity and magnetism. Okay, so look at the diagram. Why does Tom not fall over when he leans on the wall? This is because he's leant against the wall with a force F, represented by the red arrow. Now forces normally come in pairs. So for the force F, represented by the red arrow, there's also the force minus F, which is represented by the blue arrow. It's got a minus in front of it to show that it's acting in the opposite direction. These forces are equal and acting in the opposite direction to each other. The blue arrow is called the reaction. So forces will always come in pairs. One of the forces is the reaction force and one of the forces is the action force. So here we've got Tom, who is pushing against the wall, but then we've also got the wall which is pushing against Tom. Sometimes there can be more than one pair of forces acting on an object. If we take these books resting on a table, for example, the first pair of forces that is acting is the gravitational forces. You have the Earth, or the Earth's gravity, which is trying to pull the books down. But you need to remember that the books are also an object with mass, so they have their own gravity. So the book's gravity is trying to pull the Earth back. So we've got the action force of the Earth pulling on the books and the reaction force of the books pulling on the Earth. Now, as well as the pair of gravitational forces, we've got a pair of contact forces. The action force here is the contact force between the books and the table. The reaction force here is the contact force between the table and the books. Pairs of forces can also be seen when things are hanging. In this example, we've got this load hanging from a crane. And again, we've got two pairs of forces. We've got the gravitational forces, so the Earth, which is pulling on the mass of the load. And then, because the load has got its own mass, it's got its own gravitational force, so it is pulling back on the Earth. Now, as well as that, we've got the tension forces. So the mass is pulling down on the wire, but then the wire is also pulling back on the mass. When two objects collide, they exert equal and opposite forces on each other. This is another example of Newton's third law. When this car collided with the post, the car exerted a force on the post, and the post exerted a force on the car that was equal and opposite to the force the car exerted on the post. Even though the forces are equal and opposite, the effects are quite different. The car has been designed to crumple on impact. This will absorb the impact force and helps keep the passengers safe. The lamppost, however, is designed to withstand the force and stay upright, so is not being damaged as much. Okay, so now's your chance to practice some of these questions. If you stop the video, you can work through these graded questions about actions and reactions. When two things collide, they exert equal and opposite forces on each other. Collisions happen all the time in sporting activities. For example, there is a collision between a footballer's foot and a football when the ball is kicked. The force exerted by the footballer's foot on the ball is equal and opposite to the force exerted by the ball on the footballer's foot. The action of these forces changes the motion of the objects. When kicked, the football moves in a different speed in a different direction. Therefore, its velocity has changed. And because the momentum of the football is its mass times by its velocity, then the force applied during the collision also changes the momentum of the football. This is the equation that we need to remember. Momentum equals mass times velocity. Changes of momentum are often applied to vehicles. In this diagram we can see that the momentum of the cars changes as their velocity changes. In the first diagram, the velocity of this car is 0. And because momentum is mass times velocity, this also means that the momentum is 0. This car has a velocity of v, so its momentum will be its mass times v. After the collision, however, the red car now has a velocity of 0, which means its momentum has changed. It has passed along some of the force, which has caused the blue car to gain some momentum, and it goes off travelling with a velocity v. Changes of momentum not only happen when there are collisions, they can also happen when there are situations called explosions. This is an example of an explosion. We have the two skaters here that are stationary. Then we have got Sadie who pushes Ben in the back, and Ben moves forward. Ben's back exerts an equal and opposite force on Sadie's hands, and Sadie moves backwards. This is called recoil. Recoil can also be seen when a gun is fired. Before the gun is fired, both of the objects are stationary. When the gun is fired, the bullet travels out of the barrel at high speed, and it's got a lot of momentum. The gun recoils in the opposite direction. It has the same momentum as the bullet, but it's got a lot greater mass, so its velocity is smaller. It still moves with a significant force, and this force can be felt by the person who's firing the gun. Rockets work in the same principle as an explosion. So the rockets have got rocket fuel inside the combustion chamber. This means that the particles have got a very high energy and they move very, very fast. Inside the chamber, the particles crash into the sides, causing a high pressure. The hotter the gas gets, the faster the particles move, and the higher the pressure. The pressure can also be increased by reducing the volume of the gas, but this is not very practical. Some of the particles escape out of the bottom of the chamber. The force pushing these particles out is the same as the force pushing the rocket up, so the rocket accelerates upwards. Inside the combustion chamber of large rockets, the pressure is very high. As the particles strike the walls of the chamber, they bounce off, changing their momentum. There are a large number of collisions each second. This high frequency of collisions leads to a high rate of change in momentum, so a large force is created. In order to ensure that this force is large enough to lift the massive rockets carrying satellites into orbit, the exhaust must contain a large number of gas particles moving at very high speeds. This is achieved by rapidly burning a large volume of fuel at very high temperatures. For rockets that take people and objects into space, the mass of fuel is a very large proportion of the total mass of the rocket. The total mass of the space shuttle at takeoff is about 2,030 tonnes. The total mass of fuel is about 1,750 tonnes. Gas particles leave a shuttle's engine at over 4,000 metres per second and at temperatures of over 3,000 degrees C. The shuttle burns over 1,000 litres of fuel per second. All this allows the rocket to have a force which is great enough to overcome gravitational attraction and lift the rocket into space. So, important things to remember is that momentum equals mass times velocity. So the faster the particles are moving, the more momentum they have and the more force they exert. And that large rockets need to burn a lot of fuel at a very high temperature in order to escape the Earth's gravitational field. If we want to calculate momentum, we need to use this equation. Momentum equals mass times velocity, using the symbol P for momentum. The units for momentum are kilogram meters per second, and then we have mass, which symbol is M, its units are kilograms, and then we have v for velocity, which units are in meters per second. If I put this equation into a triangle, then it allows me to be able to rearrange it to work out any quantity within that equation. If you pause the video now, you can use that equation to work out which of these objects has the greatest momentum. Remember that mass is in kilograms and velocity is in meters per second. The total amount of momentum stays the same. For example, if two moving objects collide, their total momentum does not change. This is the law of conservation of momentum. As long as there is no external forces acting, the total momentum stays the same in explosions and collisions. This is the law. The total momentum before the collision equals the total momentum after the collision. To work out the momentum before the collision, we do mass times the initial velocity, which is u, and to work out the momentum after the collision, we do mass times v, which is the final velocity. If more than one object is involved, which is very likely there will be, you need to add the momentum of each object together, both before and after the collision. So with object 1, we would have its mass times its initial velocity, plus object 2, which was its mass times its initial velocity, and then after the collision or the explosion, we've got the mass of object 1 times its final velocity, and the mass of object 2 times its final velocity. To do these calculations properly, it's quite useful to have a diagram. And you often have a diagram that shows the situation before the collision and the situation after the collision. This helps you visualise what you need to do, and it can also help you visualise where the numbers come that you are going to use and put into your equation. Now in this question, we've got a silver car with a mass of 1,000 kilograms, travelling with a velocity of 50 metres per second. And we've got the green car with a mass of 800 kilograms, travelling at a speed of 20 metres per second in the same direction. Then after the collision, the silver car and the green car are in contact with each other. So we can now class them as one object. So that means the mass of that new object becomes the mass of the individual cars added together. So the mass of this object is now 1,800, which has come from 1,000 plus 800. And the question is asking us to calculate the speed that the two cars move away with. In order to solve this, we need to write down the equation that we're going to use. We have m1 u1 plus m2 u2 equals the new mass times the velocity. Here we're not adding anything onto that because we've only got one object now. So we'll start with the silver car as object 1. So its mass is 1,000 and its initial velocity is 50. Remember, that needs putting in brackets because you need to do that calculation before you add the next one on. Our object 2 is 800 and its initial velocity is 20, and that equals to the mass of the new object, which is 1,800, times v, which is our unknown. So this is equal to 50,000 plus 16,000 equals 1,800 times v. This gives us 66,000 equals 1,800 times v. So to get v by itself, we need to do 66,000 divided by 1,800 equaling v, and the answer is 36.7 meters per second. So after the collision, these two objects move off at a velocity of 36.7 meters per second. Okay, now this is a very similar example to the one we've just done. What you can do is stop the video, construct the diagrams showing you the situation you've got before the collision and the situation you've got after the collision, then write down the equation you use and start putting the numbers in. Okay, so did you work it out? Speed of the two cars as they move off together is equal to 3 meters per second. This is another question for you to stop the video and try. With this one, if you've been given all the values, what you have to do is show that the momentum before the collision is equal to the momentum after the collision. That way, you've shown that the momentum is being conserved. And that brings an end to this revision session on actions and reactions, momentum changes, and the law of conservation of momentum.